So we at 5.3. Please do this do now. The warm-up. Find the derivatives of the first two, and then do the parametric functions and find dy dx. Let's do this. So for the first one, it would be a lot easier to just do implicit differentiation instead of solving for y and then doing it the regular way. So I'm going to do implicit. This is going to be 6x, and because there's no y, that's done with. But over here, it's going to be -3. The derivative of -3y is -3. But because I took a derivative of y, it's y prime. You have to attach a y prime whenever. This one I'm going to leave blank for right now. That's going to be 4 times the derivative of whatever. And let me put parentheses right here. And the derivative of 1 is just 0. Alrighty, so let's do the inside. So that would be 2x times y plus, and then y prime times x squared. Alrighty, that's taken care of. So let's finish up 6x and plus 4. And by the way, I'm moving stuff to the left side that doesn't have a y prime. This part right here is going to be -8, so plus 8 x, come on, x, y, yeah, I think that's it. Alright, equal to 3, -3 y prime minus 4 y prime x squared. Alrighty. The final answer is going to be, once I factor out the y prime, once I factor out these y primes, I will just divide by whatever the entirety is. So let's do that. Alrighty, so I took all that and factored out a negative, and I divided both sides by -1 first to get the negative right here that you can see right there, and 4x squared plus 3. So that would be the derivative. So let's do the next one. For this one, I did it a little different. When I say a little different, I'm talking about this piece right here. I first took my derivative like I usually do, boom, and then we have a y, so we attach a y prime. Why I put it in the middle, I don't know. But when it came to this one, I typically factor out the 2, do parentheses, and then just do x and y. But this time I just treat it as if 2x was a thing. So I did derivative of 2x multiplied by y, so 2 times y. And then y, derivative of y is just 1 times 2x is 2x, but I attach a y prime. So let's continue from here. And to conclude our problem, I simply got all the y primes to one side, boom, factored out the y prime, and moved everything that wasn't y prime to the other side, and then divide by whatever is inside these parentheses to get all of this good stuff right here. Now you're probably thinking, what if I want my y prime to not have any y's in it? In this case, you're screwed, because you're going to have to take this entire thing, solve it for y, that's a quadratic, and then you're going to get a positive and negative, and that's no fun. Just trust me, it's no fun. Alrighty, parametric functions and find dy dx. Let's find dx and dy just for funs and giggles. Alrighty, so pretty much this is going to be 3t squared, and that's going to be 0. That's going to be 12t to the third. That's going to be 0. It's actually good talking about it afterwards. It makes sure I don't make a mistake. And to get dy dx, I just need to do dy dt divided by dx dt. So that will be, I'm just going to go ahead and call it dy dx, equal just this divided by this. So that will be, can I do it in my head? I can, it's 4t, but I'm going to just to make sure I didn't just do that really bad in my head. Does 12 divided by 3 equal 4? It does. Does t, oops, that's a squared. Does t to the third, does t to the third divided by t squared equal t? It sure does as well. Okay, that's to do now. Oh, reading. Reading is fun. Linear approximations and differentials. Local linearity and linearization of a function. If a function is differentiable at x equals c, then the linear function Lx containing c f of c and having the slope of f prime c, the tangent line, is a close approximation of the graph of f for the values of x close to c. Linearizing a function f means approximating the function for values of x close to c using the linear function. Local approximation, we know what a point slope is. The point slope is this form right here. And if we're gonna plug in for stuff that they've given us right there, you would end up getting, so your y1 would be f of c, and then your x1 would be c, so that's why we have c right here, and we have f of c right there. And your f prime of c would go right there. All right, so let's see what that looks like in practice. So, for 15 minus x cubed, find the equation of a linear function that best fits f at a point 2, 7. Find the error in approximating f of x by using this linear function for values of x close to, use this, this, and this. From the previous thing we just looked at, I know I'm going to definitely take this equation, take the slope of that. So we're going to get like a negative 3x squared and whatever. And then we're going to plug in this point in order to get a fc, f prime of c. I mean, at this point, f2, f prime of 2, and then 7. And I think that's all we're going to... Oh, we're going to make a line out of it and all that good stuff. So let's see what that's going to look like. So I took the derivative, there's the derivative, I plugged in my 2 to get f prime of 2, which is this. And then I kind of plugged in values. We were told to, this is going to be the 7 I was talking about earlier. We have our f prime of 2, which we now know is negative 12, and then we plugged in the 2 right here. So this is a line equation, and we're supposed to approximate at certain values, approximate at this, this, and this. So this is a line equation, by the way. So when I put 2.1, you're going to get 5.8. Just plug in your calculator and you find it. 2.01, you get... So apparently the closer you get to 2, the more accurate the number is going to be. Because if we actually were to put in these values, you can see that 5.8 is a little bit far away from 5.739. And then, let me use a different color. 6.88 is getting a lot closer. I mean, at this point, it's super close. From here to here, that's like 0.06 away. But from here to here, that's only 0.2. I think 0.02. If I'm doing stuff in my head. No, not 0.02, 0.002. And then from here to here, yeah, I don't even want to try to 0.00001 or something like that. Anyways, the closer you get to the number, the better your linear approximation. So, just to summarize it up, take the function, take the slope for it, or the derivative, plug in the point that you're talking about, and you're going to have a slope. Use your slope and the point to make the tangent line, and you can see that as you get closer to the where the tangent line is centered around, you're going to get a much more accurate value comparatively. So you don't want to use this linear approximation if you're trying to estimate at 5 and then you center it at, let's say, 17. It's going to be very off, depending on the function. All right, so we have another one. Let's go over it real fast. If the function sin x, write an equation for a linear function that best fits x equals 1. Use the linear function to approximate f of 1.02. What is the error in approximation? Oh, in the previous one we didn't even talk about the error of approximation. We'll do that here. So you first start off with writing down the function, and then you want to find the slope of that function. The slope of that function is going to be cosine. And I don't have it written down anywhere. Oh, I do have it written down right there. And you want to plug in what 1 would be into that. So you have your f prime of c. Then you're going to need your f of c. In this case, it's whatever sine of 1 is. Sine of 1 is this value right there. And then you're going to need your c, which is just 1. So plug in all your values into your equations. You should end up with a linear equation like this, simplified to this one right here. Now, the reason why they say it fits best at x equals 1 is because if you plug in 1 in there, you get the exact value, since it's centered at 1. But when you move away from 1, it's going to become less and less accurate. So let's see how accurate we would be at 1.02. So let's plug in 1.02, and we get this value. And to find out what our error would be, we plug it into the actual function, see what it actually is. In physics, we would probably use the percent difference, but I think in calculus we just simply get the difference. But make sure it's just the absolute value. So whether you put this one minus that one or vice versa, it doesn't really matter. So it would just be this difference, and I don't have much space to actually write it. 0.85211. So find out what that difference would be between the two, and you have your error of approximation. Our error of approximation would just be this value right there. Also, I know that we usually like to have 3 decimals. For this particular one, just do the subtraction and write down everything that you have. That would be totally fine with me. Sometimes you get easy problems like this, which don't turn out to be easy, because some people expect to take the derivative and stuff. But over here, you have a differentiable function f that has property where when you plug in 5, you get a 3. The derivative of that would be 4. What's the estimate for 4.8 using the local linear approximation for f at x equals 5? Well, in this case, it pretty much gave you all of these values. This right here, if you remember correctly, that was your y. This right here is your x, and then this one right here was your derivative when you plug into the derivative. So you have all of this stuff. All you really have to do at this point is just solve when you plug in 4.8. So plug in 4.8, which they did right there, and you get your final answer. Boom. Also, it should be noted that in this one you won't be able to do an error approximation because you don't know what the original function looked like. So finding the actual f of whatever, by the way, that should have been L, but that's okay, I don't care. Finding the actual value at 4.8 would be impossible since you don't know what the equation looks like. Okay, I've been trying to end this video twice already, but this is just bothering me. This must be changed into an approximation sign. Boo! Okay. There we go. Alrighty. You guys have a fantastic day. See you guys tomorrow.